All right, everybody. It is time to learn about another type of probability. Okay. So yes, there are two or more kinds. All right, but so far we're just gonna stick with the one we learned originally and now compare it to something a little bit different. Okay. So in my first video I made on this topic, I introduced that the probability of an event E is the number of ways E can happen divided by the total number of possibilities. Okay, now I want to give a name to that, and I want to compare it with something that's a little bit different. All right, so what I just told you is called classical probability. Okay, so you think about, like, if I roll a dice, how would that work out? You just think about it, okay? And you think, well, okay, there's six possibilities when I roll this dice, and I can calculate the odds of any event by figuring out how many ways that event can happen. All right, and I divide them. That's how it works out with classical probability, okay? Now, empirical probability is something different. Now, I wanted to compare them. I wanted this video to be about classical probability versus empirical probability to see how they're different, to see how they might be similar in some ways. All right. But empirical probability is done by observations. So classical probability is not. Like, when I calculate the probability of rolling various numbers on this die, then I just think about how it can work out, right? I don't actually roll the die to figure out what can happen. I'm aware of how it works out, and I can count the ways that the events can happen. Okay, that's classical probability. Classical probability requires no observation at all. We don't actually roll the die to figure out how this could work out. If we're flipping a coin, we don't flip the coin and so on. Okay? All right. Now, what's different about empirical probability? Okay, well, it requires observation. It requires actually doing something and seeing what happens and perhaps counting or tallying the results. All right? So in empirical probability, we are making observations, and the probability of an event E is the frequency of that event over the total frequency. Now, that one is a little bit harder to describe. If I'm going to write it down by definition here, I mean, that's the definition. That's what you would find in a book or something like that. But I think the stat cat is right that we really need to see an example to compare and contrast perhaps classical and empirical probability. That way I can show you this definition a little bit better. Okay? All right, so here's what I have to show you as an example to compare and contrast a little bit. So this time our probability experiment will be to flip a coin. Okay, so I had a coin here, and I actually did this earlier today. I flipped the coin and I got a blank piece of paper and I tallied the results. Okay, but all right, let's say we're going to flip a coin and I want to compare and contrast classical versus empirical probability. Okay, so first with the classical. Okay, let's pretend that we don't see this other side of the paper. Now, do I actually need to flip the coin to calculate any classical probabilities or to understand classical probabilities? I do not have to flip the coin to do that. I know that the sample space is heads or tails. That's what's going to happen if I flip the coin. And the probability of heads is, well, there's one way to flip a heads, and there's two total possibilities, so that'd be 1 out of 2. As a decimal, that'd be 0.5, or as a percent, that'd be 50%. And the probability of tails is also 1 out of 2. There's one way to flip heads over 2 total possibilities. Decimals 0.5, percentage is 50%. Now, I do all this. I conceive of the sample space, and I calculate the probabilities of various outcomes without ever flipping the coin. All right? We know how it's going to work out. In theory, maybe you see why it's called classical or theoretical probability. Yeah, so it's just, in your mind. Okay? All right, so that's classical probability. Now, how is empirical probability different? So the sample space, well, okay, so real quick, I'm getting ahead of myself a little bit. Remember, empirical probability requires observations. Okay, all right. So what I did was I got this coin and I flipped it and I counted the results. I got heads, I got tails, I made a tally and I totaled it all up, okay? And the first thing I found that was different in the empirical probability from the classical is that the sample space was a little different. What's the sample space? All possible outcomes. Well, here's all the outcomes that happen when I actually flip a coin. I got heads sometimes, I got tails sometimes, and then the coin fell off the table and I lost it once. I ended up finding it again, but as for a while I didn't know where it was. So, okay, I didn't factor that into a possibility over here. It wasn't an outcome in the sample space, but when I actually flipped it, it was, all right? Okay, and then the tally went like this. I flipped the coin 16 times. I counted 7 heads, 8 tails, and I lost the coin because it fell off the table once, okay? All right, now it's from these numbers that we calculate the empirical probabilities, all right? So here goes. The probability of heads was, okay, so I got 7 heads in a total of 16 flips. So that's 7 out of 16 as a decimal, 0.4375, or according to my observations, you'll get heads 43.75% of the time. And then, all right, probability of tails, well, all right, I got 8 tails out of 16 flips total. That's a decimal 0.5 or 50% as a percentage. So you'll get tails 50% of the time, according to my observations. And then the probability that you lose the coin is 1 out of 16. All right, one that happened once, 16 total trials. That's a decimal 0.0625 or a little more than 6%. Okay, these are empirical probabilities. Now, okay, do you see the difference? Really, we still express either of them as a fraction. How many times the event happened, divide by the total observations or possibilities. They're similar in that regard. Okay, they're both fractions and so on. But, I can't calculate these numbers in the empirical probability without making the observations. Now, from here you might say, well, why did you just flip it 16 times and so on? And, you might say you should have flipped it more than that. But my point is, I just wanted to do something for the video. And I want it to be real. I want it to be that I actually flipped the coin and so on. And I wanted you to see the results and compare. Okay, of course I could have flipped it more times. I could have also rolled a die. I could have done all kinds of things. But you see the difference. Now, somebody might say then, well, shouldn't these match over here? Why didn't I get 50% here, but I did over here? And my answer to that is, well, these numbers don't have to be the same, right? What if this coin is not fair? What if it's, I don't know how they do this, but I'm pretty sure you could get coins that are biased towards heads or tails. And I'm not sure if they're weighted or what, but it might be that when I'm just thinking about it, I think that there's an even chance of heads and tails. But when I actually flip it, maybe the tails shows up more often, or maybe the heads does. Maybe there's something weird about the coin, okay? So they don't have to match, all right? But there is this connection between the two of them, okay? So if you're wondering, is there a connection between the classical and empirical probability? Well, there's something called the law of large numbers. Okay, I forgot to write the name of this, but the law of large numbers. It's kind of it's a law in the sense of this is the way the world tends to work out. And it says, as you repeat an experiment many times. Now, when you hear experiment, you can think of observation, okay? So this is like an empirical probability right here. As you repeat the trials, as you flip the coin more and more and more times, and you observe what happens, that's what that says. The empirical probability that you calculate will approach or become equal to the classical probability. Okay? So like whatever the correct classical probability is, you know, if I was correct about this coin and it was a fair coin, then the empirical probability, the more times, say I flipped it 20 times, say I flipped the coin 50 times, as I do that more and more, these percentages will even out to be equal to those. All right. Now, what the law of large numbers doesn't say is how many times you have to run the experiment. It just says the more times you do it, the more this calculation becomes equal to that one.